This video is about the geometry of vectors. Now, as always, begin by reading through the textbook and taking some careful notes, but now consider the following highlights for this topic. We'll begin with just some basics of vectors, such as what is a vector? Well, a vector is a geometric object that has an initial point. And I have a diagram here to describe this. And my initial point is labeled with a capital A. And then from that initial point, we have a line segment now extending across our page to what's called a terminal point, which I've labeled with a capital B. And then the direction of the vector is noted or denoted by an arrow that you can see in the diagram. And that arrow indicates the direction. So where does the vector start and where does it end, such as the initial and the terminal points. And then the notation for such a vector could be labeled as two capital letters indicating the initial and terminal points. We've labeled those A and B. So you could have a capital A and then a capital B in order, first and second, with an arrow over the top of them indicating the direction of the vector. That's just a commonly used notation for vectors. Now, the magnitude or length of a vector is denoted by what you might think of typically as an absolute value symbol. In algebra or just math, arithmetic, we use absolute value symbols where you have two vertical bars containing something. And that's the same notation used here for magnitude of a vector. But then within those absolute value or straight vertical bars, you have the label for our vector AB. All right, that would just represent the length of such a vector. Let's add a couple other notes. One being that two vectors are considered equal if they have the same magnitude and direction. So equal not just in length, but also direction. Or secondly, note that vector notation can involve the initial and endpoint letters with an arrow over them as described already. Or textbooks sometimes use a single bold letter to name a vector, such as just a lowercase u or a lowercase v might be commonly used letters, but they're in bold print, which is actually a little bit challenging to do when writing by hand. So when writing by hand, we can also use a single letter with a half arrow over it for convenience, such as instead of a lowercase bold u, I'll draw a lowercase u, but then with a half arrow over the top of it, meaning like only one of the maybe branches of the arrow you might see done. It's just more efficient to write half of the arrow, I suppose, when writing by hand. But the point is that it's actually challenging to write a bold letter by hand. And so rather than doing that, we're going to use the arrow notation where you have a half arrow over a single letter. Now, next, let's note that adding two vectors geometrically, and geometrically meaning like basically by picture or by construct, can work as follows. We're going to draw an example of this. Now, to do so, we're going to have to create some vectors. So I'm just going to make some up here. And it's hard to do or hard to convey what I'm drawing, but I'm going to describe it. So I'm going to draw a single arrow that's slanted upward to the right, a certain amount of space. And so you can imagine a diagonal arrow that starts somewhere lower to the left and ends somewhere upward to the right. I'm not going to label the initial and ending points on this vector for now because we're just looking at the geometric construct of this. So there's a vector, and I'm going to label that or call that vector u, and I'll label that with a lowercase u with a half arrow over that u. So that's vector u. I'm just kind of creating or saying, let's let that be vector u. But then I'm also going to create another vector so that we can put a couple of them together here in the page. And this other vector I'm going to draw in kind of a different direction. So I'm going to start lower to the right. I'm just doing this next to vector u that I just drew. Lower to the right, but then kind of moving upward to the left. And I'm going to make it a little bit shorter than vector u, but still kind of upward to the left, diagonally drawn. And this will be vector v. So I'm going to draw this or note this with a lowercase v with a half arrow over it. Again, we're just kind of saying let that be vector v. Now, if I wanted to then do some geometric addition of these vectors in the way that I would write perhaps vector u plus vector v, then we can do this geometrically by taking the first vector in the pair, so in this case vector u, and redrawing it. Now we have to do this pretty close to exact. So I'm going to draw a copy of vector u to the best of my ability that's the same direction and same length as u. Then if I want to add vector v to that, where that first vector u ends, I'm going to begin vector v and draw an exact copy of that one. Again, same direction and same length. To the best of my ability, we're just hand drawing this, right? But again, the way that v was given, we're going to try to copy and draw in our picture now. The important thing is the order in which these start and end. So notice now, to do vector u plus vector v, we started by drawing vector u, which let me label here. We have vector u first, and then where vector u ended, we started vector v and then simply let that vector extend in the same direction and for the same length that it was originally given. What that creates in our picture now is, you could say, a starting point for vector u, where we began the whole thing, and then an ending point for vector v, where we ended the whole thing. If we were to connect the starting point of u with the ending point of v, which creates then a different vector, that is vector u plus v. So simply putting them together in order gives us a geometric addition of those vectors. Now, it's probably also fair to note that the order in which you put the vectors doesn't actually matter. So turns out vector addition, even geometrically, is commutative. What I mean is, let's go to the initial point we started with in our diagram, which we had as the initial point for vector u in this previous attempt here. But first, what if I had extended from that same point vector v first? So vector v, same direction, same length. Again, I'll just estimate that by hand. So now I'm starting with vector v, but then if I would have put vector u from where that one ended, it should take us to the exact same ending point we had the first time. The point being that there's actually commutative property here in this addition of vectors. You could start and end with either vector, first or second, and end up at the same ending point for the entire addition. All right, and that's just a geometric look at a vector addition. Next, let's discuss multiplying a vector by what's called a scalar. That's S-C-A-L-A-R, scalar. A scalar is just another name for a number, a real number. In this case, how we're going to multiply a vector by a scalar is by starting with a vector. So let's draw a vector. In fact, I'm going to draw, I'll try to copy the same vector u I had drawn in the previous example. So same direction and length approximately. Again, drawing by hand is not perfect. Let's do our best with that. And if that's vector u, then what we can say in order to do some scalar multiplication is that, for example, I could take, or I could try to describe 2 times vector u, and all that would mean is I want to double the length of the vector. So instead of vector u, same direction, but twice as long. And again, we'll approximate this to draw it according to what we drew for the first time for u. But if vector u is 1 inch long, then vector 2u is 2 inches long. That's what it means to double or multiply the vector by a scalar. Of course, these scalars could be any real number. So like, what if I did 1/2 u? Well, that would be half the length of the original vector, which I'll again estimate. So if the original vector was 1 inch long, then this one is now 1/2 inch long. It's half of the length of the original, so 1/2 times vector u. Or you could even multiply by a negative. So like negative vector u would simply move in the opposite direction, but be the same length. So we'll try to match the opposite of the direction that the first vector was drawn. Again, you're just estimating if drawing by hand, it's never perfect. But that estimation in the opposite direction, but same length, would be negative for the scalar of a -1 times u. So again, these are just some geometric looks at some arithmetic with vectors. Let's try some examples now using this kind of arithmetic with geometric or drawn vectors and see what else we can develop. Our first example says, sketch the vector indicated, and then it says the vectors u and v are shown below. So what we're seeing is a diagram with this time at least some graph paper, which helps us stay a little bit more accurate in our drawing. And this graph paper grid, just located at the origin, has a couple vectors in it. We'll call one of them u. I'll describe these in 1 second. And then another vector also drawn on the same grid as vector v. Now, vector u starts at the origin and extends up 2 units left and 3 units up. So its terminal point would be at the point -2, 3. And vector v starts at the origin, also 0, 0, and extends up to the right in quadrant 1 with a terminal point of 3, 4. All right, so those are just given vectors, but they're at least put on graph paper so we can get a little bit more specific on the direction of them. Now, what we want to accomplish is listed below with some other graph paper grids for us to use. And the first of those, example A, being we want to add vector u plus vector v. So that's what we're trying to construct, again, given the u and v as provided in the first initial set of graph paper. We're going to use those, but now put them together in an addition form. Well, we just discussed or drew these, but without the graph paper. This time we're going to use the graph paper. And so if we're starting with vector u, then I'm going to just copy the diagrams that we had previously drawn just to preserve some of the accuracy here so it's actually looks correct. We take vector u, and I'm just going to copy that and paste it into our new grid here. So it's starting at the origin, just like it did, and it's extending to the point -2, 3. All right, so we have that drawn. I'm just copying it into our picture. From that one, then, to add on to it vector v, where vector u stops, we're going to begin vector v, which again I will just copy for the sake of accuracy and bring into our diagram. Now, this extends a little bit beyond the graph paper. So, in other words, the grid I made was not quite big enough to accomplish this, but you can still see it here enough, I believe. So, you're starting at the origin, for example here, example A, where you're trying to add vector u plus vector v. We start with, I'm going to label these or draw these on here. So we have vector u drawn from the origin to the point -2, 3. And then from where that point ends, that is -2, 3, we're beginning vector v, which extends the same measure it was originally. So that would be 3 units to the right and then 4 units up. But that's starting from where the vector u ended. Now, the resultant vector of those, we'll go ahead and draw, which begins where the first one did at the origin and ends where the second one did at its point. And if we draw this in, so we're going from 0, 0, where the initial point was for the first vector, up to where the second one ended, which is not labeled, but we could find it rather easily doing just the geometry of our diagram. That resultant graph, or vector we just drew now, would be the sum of those two vectors. Now think about this for a second. If I wanted to find out where exactly that resultant vector ended up, can you think of a way that we could actually figure that out? Just think about that for a second. There is a way, but look at the picture and figure out what would that be or mean. How could I find out exactly the point where that vector, the second one, ended, so that it's the terminal point of my sum of those two vectors? Okay, just think about that for a second. Now let's move on to the next one. Our second example is trying to have us draw vector v minus 2 times vector u. Well, again, we'll just kind of go in order here. If you start with vector v, then again, for accuracy, I'm just going to copy the vector v we had drawn originally or initially and put it in our picture, which started at the origin. So I'll do the very same thing. And of course, this vector, as originally drawn, extended 3 units right and 4 units up, ending at the point 3, 4. So we'll copy that into our picture, our graph diagram here for part B. That's vector v. But now I want to subtract from that 2 times vector u. Well, remember, we discussed above that with scalar multiplication, negative just means the opposite direction, and 2 means twice its length. So what I'd like to do now is draw, and I'll try to use some accurate arrow to do this, 2 times vector u, so twice as long, and in the opposite direction. So notice vector u originally went left 2, up 3. So that length has now to be extended twice in the opposite direction. So that means you could go right 2, but then down 3, but do that twice. Now that's going to take us off of our graph paper grid, but that's okay. If I start where the vector v ended here in our diagram at 0.34, and I go the same amount of length in the opposite direction, but twice. So down 3, 1, 2, 3, right 2. That's like one of the u vectors. But if I do the same thing again, so down 3, 1, 2, 3, right 2, again, it's going to take us off the grid a little bit. That would be twice then u in the opposite direction of the original u. So that now, if we write these in, just to make sure we're labeling and understanding what's going on clearly, we started with vector v, graphed in its original direction and length, and then from where v ended, we then began tracing out negative u, but twice. So there's negative u the first time, and then negative u the second time, so twice. That takes us to a place where we ended them, but then that's the final point. So if I now draw an arrow from the beginning of where v was to the end, just let me get the color correct here. So from the initial point at the origin, now to the ending point where our second u ended, that would be the vector v minus 2u. We started with v, then we took away 2 u's from it. All right, so this is, again, just a geometric look at vector arithmetic. So in the first diagram where we had u plus v as this gray vector, this third one, after putting them together, that is really vector u plus vector v. In the second diagram, we started with vector v, and then we took away from it 2u where it ended, and that result then would be vector v minus 2u. And that's how we can do a geometric construct. Now, you may be wondering, as I asked the first time, could you find the point where the combination of these ended, right? Isn't there a better way to describe these with more symbolic language or work so that we don't have to worry about or rely on the picture? That question should be kind of floating in our minds as we're struggling to draw these very well.